Kind regards to the chair, Professor Dr. Samha El-Bitagi, and to the audience. I am Javier Aramayo, and I will be conducting the presentation of our work entitled A Generative Adversarial Network for Data Augmentation, the case of Arabic regional dialects, developed in collaboration with Professor Ashraf Elnagar and Professor Mohammed Lataifeh, and thanks to the Research Institute of Science and Engineering of the University of Sharjah, as well as the IASTE exchange program. Our presentation has the following content: introduction, related work, datasets, and generative models, covering the whole dataset and the model that we use, that is Centigan, the experiments and results, and the conclusions. In this slide, I will be showing a brief summary about our work. Some remarkable points are the following. We decided to implement a Generative Adversarial Network, or GAN, since they have proven to be so effective in text generation. We specifically used the sentimental GAN, or Centigan model. We adopted a modified version of this model in order to generate sentences for 5 regional Arabic dialects: Egypt, Gulf, Maghreb, Levant, and Iraq. The main objective of our work is to overcome the scarcity of region-annotated dialectal Arabic datasets, or DAs, by automatic generation of such corpora. The DA generation process for a specific dialect relies on a generator to create new text and a discriminator to evaluate it, with a dynamic update that will allow the process to run automatically without any supervision. Novelty and diversity are the two metrics that we decided to use, since they can verify the consistency and quality of the generated DA text, and also they can provide information about how new and how diverse is our generated dataset. Experimental results confirm the reliability and value of the generated datasets when tested by different classifiers. With these experiments, we can confirm that the generated text is keeping the most valuable information from any different dialect. Before starting with the main part of the presentation, it is important to give an explanation about how GAN works. These models were first introduced by Ian Goodfellow some years ago. They are composed of two different networks called generator and discriminator, commonly CNNs. The generator objective is to learn the common features for images, or text in our case, in a dataset and generate new ones with similar features as in the original data. The discriminator job is to validate and classify these images as real or fake. This process is called adversarial, since the generator is trying to fool the discriminator while the discriminator tries to improve in order to distinguish between the real and the fake data. Based on the training process that we explained before, one of the most recent works on text generation is Centigan. We decided to use a Centigan-like model with some modifications in order to improve our results. When populating raw resource dialects, we used one generator per class as well as multiple discriminators instead of a single one as in the original work. The Arabic language is the official language in 22 countries, located primarily in the Middle East and Africa. Within each country, there are variations from the source. Arabic language is projected as different dialects that can be classified at city, country, and regional levels. The objective of our work is to build richer datasets for DA that maintain the main features of the original colloquial text, while generating diverse novel sentences. Apart from GANs, there have been many different approaches and models used for text generation. Some examples are the recurrent neural networks, or RNNs, bidirectional encoder representations for transformer or BERT, and the generative pre-trained transformer GPT-2 and GPT-3, being the state-of-the-art in this topic. Most of these models cannot be used as they suffer from different structural and algorithmic limitations, in addition to the large dataset often required for training them, in the case of GPT-2 and GPT-3. GANs were proposed as a solution for the problem stated before and for being better suited for the scope of this work. As before, there are some models that use the adversarial algorithm. Some of these are SecGAN, RunGAN, MaliGAN, and LeakGAN, being so similar between them. For this work, however, we adopt Centigan, being the one with the best performance overall. It uses an LSTM layer as a generator, and as a discriminator, it uses a convolutional neural network, a CNN. In the following slides, I will be showing information about our dataset and the generative model that we used. We decided to use the Madar dataset, since it covers the dialects for 25 cities from the Arab world, created by translating selected sentences from the basic travel expression corpus. The regional datasets were compiled by collecting several sources of data from cities that make up a specific regional dialect. In order to prepare the datasets for training the GAN, every sentence is cleaned and limited to a minimum length of 2 and maximum of 18. The punctuation marks Latin and American were removed, as well as Latin characters and numbers. The regional group comprising of 5 specific datasets were Egyptian, Gulf Arabic, Maghrebi, Levantine, and Iraqi. Some statistics about our dataset can be seen in Figure 2. The most populated set is Maghrebi Arabic with over 30,000 sentences, while the least one is Iraqi with only 5,000. This distribution is important to show how the model performs under different situations. The next section is about the model that we used. As we stated before, it is a modified version of Centigan that can be seen in Figure 3. The main difference between the original work and our model is that we decided to implement different discriminators instead of only one. This with the purpose of improving the quality of the output in sentences. As well as with the network, the algorithm was also modified. It starts with a pre-training stage of both. The generator is trained first by using the MLE algorithm, the maximum likelihood estimation, while the discriminator is a classifier. After this stage, both are ready to start the adversarial training. The loss function used in both cases is a modified version of the Wasserstein loss. After the training process, it was possible to generate a huge variety of sentences of different lengths. To show the effectiveness of the algorithm, we explored a subset of 2 sentences generated in different regional Arabic dialects. To have comparable results, all selected examples are on the subject of reserving a room in some hotel. The generated sentences in Table 1 reflect the use of specific words from each dialect, highlighted in red, which makes it easy to identify each subregion. I will now provide some seconds to let you check the examples that we are exposing here, as well as verifying the highlighted words that we are specifying for each dialect. In order to determine whether the generated dataset is useful to expand the original set, we considered 2 different metrics, novelty and diversity. Novelty evaluation is carried out to ensure that the generator is creating new sentences instead of copying the ones in the dataset. It's a metric based on the Jaccard similarity function, so it compares every single sentence in the generated set with every single sentence in the original dataset. On the other hand, diversity measures how different are the generated sentences between each other. We run diversity for the generated and from the original sentences in order to show the difference between them. The average results for novelty and diversity are shown in Table 2. In both cases, a higher value means more novel and diversified sentences. In the case of the diversity column, we have 2 values. The one on the left shows the result for the original dataset, while the one on the right shows the result for the generated sentences. Another experiment that we consider important is the classification process. A classifier can provide useful information about the performance of our generator, and also determine whether the generated sentences are useful to expand the original dataset. Another key point about the classification process is that it will show us how good is the generator replicating the information in the original dataset by using the most common words from each dialect. In order to do so, we used 4 different classifiers: a support vector machine, a multinomial naive Bayes, a long short-term memory network or LSTM, a general deep neural network, and a convolutional neural network. We also explored 4 different scenarios to show how the generated data is improving the classification process. The first scenario was to train and validate on original sentences and test on original sentences too. The second was the same, but we added the generated sentences for training and validation. The third is to train and validate on generated sentences and test on original sentences. The fourth and the last is to train and validate on original plus generated sentences and test on generated sentences only. The reasons why we decided to implement these 4 scenarios are the following. The first will show the initial expected performance for a classifier trained only using the original dataset. This information is helpful to study the impact of adding the generated sentences in the second scenario. Similarly, we study the third and fourth scenarios but testing on generated sentences. It should be noted that the amount of available data for regional dialects is satisfactory for building robust classifiers. However, our aim here is to study the quality of generated sentences. Therefore, we created a dataset that is composed of original and generated sentences. In this slide, we show some information about the amount of sentences that we used in each scenario, as well as the results for each classifier in terms of loss and accuracy. It is important to remark that all the results in Table 3 are for the testing dataset. As it can be seen, the second experiment improves the results of the first, showing that the generated sentences added to the original dataset provided useful information to the classifier. Being important not to forget that both experiments were conducted on original sentences for the testing dataset. Exploring now the third and fourth scenario, we can see that the accuracy score in both cases is higher than in the previous ones. It is important to mention that the high accuracy results testify that when testing on generated sentences, the classifiers performed better when compared to original sentences. This means that the generated sentences better capture the features of each dialect. In this last slide, I will show the conclusions of our work. In this paper, we used a modified version of Centigan to enrich low-sized datasets by generating a diversity of high-quality sentences for 5 different Arabic dialects. The number of generated sentences was higher than the number in the original dataset, as we expected. The procedure reduces the vocabulary size and only uses the most common words. Although the reduction affects marginally the diversity of the generated text, the detected features are key to each dialect, which results in robust classification performance. The novelty score is very satisfactory for all the generated datasets, which suggests that the generative process is capable of producing new sentences based on the detected key features. Experimental results demonstrate not only the consistency and effectiveness of the word generator process, but also the enhancement of classification results when using the original and generated datasets. The improvement in the accuracy score is significant, as shown in the experiments. With these conclusions, we finish with the presentation. Thank you so much for attending.